all of the examples that we've seen so far dealing with ionization energy have all been about just the first ionization energy, when you take that first electron away. That as you go across the periodic table, the first ionization energy goes up. Because again, the increase in the nuclear charge, the number of protons, but the valence electrons are in that same shell. They occupy the same shell. And as you go down the periodic table, the first ionization energy decreases because, again, the distance, the valence electrons are in shells that are further away from the nucleus, and that decreases the attraction, making it require less energy to take an electron away. Now, today we're going to talk about what if you after you take the first electron away, and then you take the next electron away, and now you're to the second ionization, and then maybe to the third ionization, etc. So it does continue. So it is possible to remove more than just one electron. And obviously as you remove them, it gets progressively more and more difficult, or requires more and more energy to remove the next one. Okay, because as you take electrons away, the electrons that are left now feel a stronger attraction to the nucleus, and so it takes more energy to remove them. That's what that first paragraph here is talking about. Okay? Now, what you notice, though, and you've seen this probably in general chemistry, is that you'll notice this blue area right here where you see not just an increase, like let's look at aluminum. Aluminum goes from 578 to 1800 to 2700, but then, so this is taken away. Here's the first ionization energy, the second, the third. But then for aluminum, notice that by taking that fourth one away, you see, again, a big jump, okay? So let's talk about the big jump, because it happens in all of these, but you'll notice it happens at different ionizations. So using sodium as an example, this large jump in the data between the first and the second ionization energy shows that, again, for sodium, the first ionization, it doesn't take a lot of energy to remove that first electron, but the second electron takes almost 10 times as much energy. Okay, and this is because, and this is how you're going to explain it on the test, because the first electron removed from sodium is a valence electron, and it's shielded by all of those inner shell, those core electrons. But since sodium only has one valence electron, once you remove that valence electron, the next electron to be removed, remember sodium, 1s2, 2s2, 2p6, 3s1. So once you take that electron away, it's gone. What's the next electron you're going to take away is one of those 2p electrons. So now you've gone from the third shell all the way into the second shell. And that second shell, as we learned from Coulomb's law, is much closer to the nucleus, and so feels a much greater, a much stronger attraction to the nucleus. Okay? So that second electron in sodium is what we call an inner shell, or a core electron. And so it's much closer, it's much more attracted to the nucleus, and therefore requires more energy to remove. Okay? And notice for all of the elements that's the case, is that once those valence electrons are gone, for example, aluminum is 1s2, 2s2, 2p6, 3s2, 3p1. So these are the valence electrons. They're in the third shell, and once those three are gone, 1, 2, 3, now what are you removing from aluminum? Those are gone, so now you're into the second shell. And again, that's why you see that great big jump. Now what this does is it helps us to identify elements. That when you see this big jump in ionization energy, you can tell, oh, that's where it switches from valence electrons to those inner shell, those core electrons. And so we can identify elements based on this ionization energy data. Okay, so let's look at this one right here. So it says an element in the second period. So first of all, second period is lithium over to neon, right? Look at your periodic table. Lithium to neon. And it says it has the following ionization energy data. Identify the element and then justify your answer using data from the table. So really what you're looking for is, when do you see the big jump? Okay, and again, don't look at what you're looking for here is, for example, from 419 to 3000, That's a jump of almost 2,500. Well, you're like, well, yeah, but 5878 to 7975, that's also, about 2,000. Okay, but compare that. I mean, you started at 400 and you went to 3,000. That's an increase of like 7. From 5878 to 7975, that's an increase of maybe 1.3, 1.4. I'm just, not very much. This is an increase. This is a 7 times increase. This is a very slight increase compared to that original number. So you're looking for, where do you see that big, jump? Notice on the sodium one, it was 496 to 4560, something like that. That's almost a 10 times jump. And there will be one that is clearly much, much larger than the rest. From 3,000 to 4,400, that's about a 1.5 jump. Again, you don't even need to do the math. It's going to be really, really obvious here. Where is the biggest jump in terms of ionization energy? So this element loses one electron fairly easily, but the second electron takes way more energy. And so therefore, it only has one valence electron. And if it only has one valence electron, then you look in that second period. What's the only element from lithium to neon that has one valence electron? And if you're having a hard time with that, remember that valence electrons go 1, 2, 3, 4, 5, 6, 7, and then 8. So the only elements that have one valence electron are in that very first column. Okay, the elements that have two valence electrons are in the second column. Okay, and then over to boron has 3, the fluorine group all the way at the end has 7, and then the noble gases other than helium have 8. Okay, so what is it? What element is it? It's lithium. Of course it is. Okay, and how do you justify that? Because you would just explain those two numbers right there. The low first ionization energy indicates that lithium has one valence electron, but then the big jump to the second ionization energy shows that there's just one valence electron, and then that second ionization energy has to be an inner shell electron. I'm not going to write all that out, but you should pause it and write all of that out. Okay, so I would just say the big jump between the first and the second ionization energy shows that lithium has one valence electron. And the only element in the second period that has one valence electron is lithium. Okay, here's another example. Iodine can react with a certain element M. Again, just a made-up pretend element. So iodine can react with this element. The successive ionization energy values for element M are given below. So we're looking at here, 738, 1451, 7733, 10,000, and 13,000. Okay? So we're looking for where do you see the biggest jump? Okay? To me, the biggest jump happens right here. Okay? You're going up by 5 times roughly. Here you're doubling. Here you're going up, not even doubling. Here you're not doubling. But here, absolutely that jump right there. So that to me tells me that this atom has 2 valence electrons. Okay, because the first and the second are fairly easy to remove. So that means 2 of them are on the outer shell. But then that third one, that's when you're getting into the much more challenging ones. So part A says, what is the charge of the ion formed by element M in its compounds? Justify your answer in the data table. Well, if it has 2 valence electrons, we know that based on that information and my beautiful drawing up here, that it has to be in this column. And what charge do those always have? What's the most common ion of those? Is it's going to lose those 2 valence electrons because it doesn't take a lot of energy to do so. So what is the charge of the ion? It's +2. Okay, and whether you write 2 plus or +2, it doesn't matter. Okay, and then how do you justify that? Again, talk about the big jump being between the second and the third. So that means it has 2 valence electrons, and therefore the third ionization is you're removing an inner shell electron. Okay, and then part B, given the charge determined in part A, what is the formula for the compound? Well, if it's M, here we go back to unit 0, right? M2+, and iodine, what charge does iodine always have? minus 1. What is the formula of the compound then? Well, it would be M. This 2 comes down here, so it would be Mi2. Okay, does it say to explain it? Nope, so I'm not going to. Mi2, that's my final answer. I'm done. Okay, example 3. The first ionization energies for element X, for metal X, are shown in the following table. So we know it's a metal, and metals always lose electrons. Okay, the ionic compound XF3 is not known to exist. Explain why using the data in the table above to support your explanation. First of all, I'm going to clarify one thing here. This is from an old AP test, and the College Board did admit we made a typo. Okay, and hopefully you can see that typo right here. Okay, there's no way that that fifth ionization energy would be less than the fourth. So the correct, let's just make up a number. Let's say that's 15,600. Okay, the problem is you see that, and they very, very rarely make typos. This happened in the testing year of 2020 when school had gotten canceled and they were in a big rush to make all these questions. So very, very rare for them to make a mistake, but that should not be 13,600. And hopefully you would see that and go, wait a minute, that doesn't seem right. But again, to me, the big jump happens right there. Yeah, it doubles. Yeah, it goes up, doubles there. There it dropped a little bit, which is weird. I don't know why it did that. But to me, that's the key, is that, it has, therefore, we know the big jump happens between the second and the third, so it has to have 2 valence electrons. So this X has to be X2 plus, and we know that F is F minus, so therefore the compound it would form, because it's an ionic compound, would be XF2. Okay? So explain why why does XF3 not exist? Because X has 2 valence electrons based on that data. And so the formula it would make would be XF2, not XF3. Okay, and you could talk about the big jump happening between the second and the third. That's how you know it has 2 valence electrons, etc. Okay, and that is if you follow that with ionization energy, you know the patterns for ionization energy as you go across, as you go down, and then you can look at a table to determine how many valence electrons an atom has, and then therefore what charge it's going to have. Then you are in good shape with ionization energy.